Welcome, Triglets. So glad you could join us today for the second lesson in Chapter 3. We will be looking at graph translations today. But first, let's review what we did last class, which was identify some asymptotes and recognize some parent functions. Before I give you the answers, I hope you have taken some time to do this. If you haven't, pause the video and go for it. When we take a look at these, as far as having asymptotes, we know that 1's going to have an asymptote because the variable's in the denominator only. We also know that 4 is going to have an asymptote because it's in the denominator only. We know they're going to have vertical asymptotes. What happens for 2 and 4? Well, they're going to have asymptotes also, okay? Because obviously this x in the denominator means that we have a vertical asymptote there. And likewise, x in the denominator here means there's a vertical asymptote here. That's all we're worried about today. In future lessons, what we may find out is there could be an oblique asymptote also. And that could be a oblique line because these degrees are equal. So there might also be a horizontal asymptote or an oblique asymptote if the numerator has a higher degree than the denominator. You don't need to worry about that now. For question number 5, read this carefully. It says you're supposed to find a graph, an equation that has one horizontal asymptote at negative 23 and a vertical asymptote at 18. At what point might you center the screen to see your calculator? So we're not looking for the equation here. We're looking for where the new center would be. So basically what we're saying is, hey, we have a horizontal asymptote all the way down here at negative 23. So here's my graph. There's the origin traditionally. Well, always actually. Okay, so I'm going to say my horizontal asymptote is no longer up there, but my horizontal asymptote is now at negative 23. And my vertical asymptote is at positive 18. So instead of having my vertex, or my center of the graph, be here at 0, 0, I now want to have my graph centered where those asymptotes intersect. So that's going to help you answer that question. So take a second, think about these, pause the video if you need to, but ta-da! These are your answers. Okay, it says to identify which, number 12, which of these have asymptotes. No asymptote, no asymptote, no asymptote, asymptote. Actually, a vertical asymptote and a horizontal asymptote. Here, if you graphed these at the top, you would see those horizontal asymptotes at 0, at 1, at 3, and at 0 again. Here are the answers to the homework from last time. I know this is very difficult because I'm not there for you to ask questions of, but when I come back, I will be staying after so you can get caught up, or you can go to the NHS Tutoring Center or ask any of the math teachers if you have questions. Okay, so what we're going to look at today is where students are going to learn the effects of translations and scale changes of graphs in order to write the equation to describe the new graph as it's related to its parent function. So you're going to want to have that hard cardstock paper that I gave you either last class or the class before. And you're going to want to keep that handy because you want to recognize what the parent functions are so you know what your equation is to start with. You will see that you do have homework, and again, we'll go over the homework just like we did today. I'll have it in the video. You can check it. If you have questions, find a math teacher. We are going to try to take a quiz next class. I won't have it graded for you as quickly as normal, but we're going to try to take that quiz next class, and you'll just do it, turn it in, and it'll be good. You do have homework on page 163, 8 to 13, and 183, 7, 8, and 12. So today what we're looking at is how is the gray graph related to the black graph. So the black graph is our original, so we're starting here. So this is our, if we go back to geometry words, this is our pre-image, and this is our image. So what did we do to the pre-image to get to the image? Excellent. Our pre-image was 0, 0, and our image is 2, 0. So what happened? Well, we moved which way? We went to the right. How many? 2. So if this ordered pair was xy, this ordered pair is x plus 2, because we added 2 to our x. Did our y change? No. Interesting. Let's take a look at another one. So we're taking a look at the pre-image, which again is the origin, 0, 0, and our image. What are the coordinates for our image? Well, 1, 2, 3, 4, 5, and then up 3. So it looks like it's 5, 3. So again, if our ordered pairs are always x comma y, well, what did we do here? Well, instead of x, we went right, so we added 5, and we went up, so we added 3. If I could find the plus sign, I'd be doing great. Does that describe it? We went right 5 units, and we went up 3 units. All right. Let's try another one. Here we're taking our pre-image, which again is the origin, and we're moving it to our image. But this time we're going left. So we went left 3 and up 1. So we went from 0, 0 to negative 3, 1. So again, if this is x and this is y, what did we do to x to get negative 3? Well, we did x minus 3. And then what did we do to y? Well, we went up 1, so we added 1. Now think about that for a second. If this is where we started at xy, we went left 3, so we subtracted 3. We went up 1, so we added 1. Okay, so let's take a look here. We have our origin again. So this is our pre-image, and this is our image. So we went from the origin, and then we went right 1, and 1, 2, 3, 4. It looks like negative 4. So how did our ordered pair change? Well, our ordered pair was xy. I figured I should type because that's easier to read. And what happened to our x? Well, our x went right 1, so we added 1. And what happened to our y? Well, our y went down 4, so we subtracted 4. So you're basically giving directions for that. They're like, Finney, this is not hard. We don't need this kind of instruction. All right. So what happens here, home slice? Oh, yeah. How is the black graph related to the gray graph related to the black graph? Well, look what they have here. These are ordered pairs, right? We took the vertex, which was 0, 0, and we moved it to negative 3, 1. Looks like that ordered pair is what moved. And all of the other ordered pairs did the same thing. So if we look at this ordered pair, let's just check this out. It went left 3, and then up 1. Hey, that's beautiful. Check out another one. This went left 3 and up 1. Hey, does it work for all of them? Let's find another pretty lattice point. Went left 3 and up 1. Beautiful. So it does appear to have worked for all of them. So what happens here is we moved our graph to the left 3 units and up a unit. Well, what's our new domain? Well, our old domain was all reals, true? The domain for this function was all reals. What's the domain for the new function? It's the same thing. It's still all reals. So our domain is all reals, or you could say all real numbers, or some of you like to make that crazy looking R thing. And then, what's our range? Well, for the parent function, look at your cardstock paper. The cardstock paper says the range for this is y greater than or equal to the vertex, right? Well, the vertex is 0, 0. Our vertex here is negative 3, 1. So what happens to our range? Well, our range was 0. What did we do to it? We added 1. Oh, so it's all reals where y is greater than or equal to, let's see if I can find that symbol. So we're going to go down here to math. Oh yeah, baby. Greater than or equal to 1. And that's our range, because we moved our graph. Okay, what happened here? Well, we take our key point, which again we have the bottom of our hook, which was 0, 0, and it moved to negative 1, 3. So our points that we're comparing are 0 and negative 1, 3, and we went left 1 and up 3. Well, what's our domain and range? Well, our domain and range for the original function was x is greater than or equal to 0, true? If you look at your cardstock paper, well, instead of it being greater than or equal to 0, we moved left 1. So here our domain was x is greater than or equal to 0, and our range was y, which is the same thing, greater than or equal to 0. So we're going to compare those original values. That's our domain and range here. What happened here? Well, we moved left 1. So this is x minus 1 and y plus 3. True? Well, it was 0. 0 minus 1 is negative 1. So our range is x is greater than or equal to negative 1. Because we just moved it left 1. What's going to happen to our range then? Well, our range used to be y greater than or equal to 0. Now we moved it up 3. So 0 plus 3, that's right, greater than or equal to 3. You guys are so smart. You don't even need me. Thank you. Thank you for needing me. Now let's check this puppy out. We got a circle here. That's not on our grid. We don't have a circle on our cardstock paper, so we kind of have to think about this on our own. So let's take a look what happened. Well, we started at the origin, and now we're over here. So it looks like we went from 0, 0 to 10, negative 2. Beautiful. Okay? So that means we move to the right 10 and down 2. So let's come over here and let's talk about what our domain was for our original circle. Domain is an x value. Looks like it's between negative 5 and 5. So if I'm going to put that down, I've got negative 5 is less than or equal to x which is less than or equal to 5. And that's my original domain. Okay? Well, let's talk about range. Let's talk about range, baby. What's our range? Well, if we're talking about the same values, okay, well, the same circle, we're talking about y's. So our y's, the lowest y was -5, and the highest y was 5. So it's the same exact thing, except with a y. So -5 is less than or equal to y, which is less than or equal to 5. Alright, so now what happened to our domain? Well, here it says that we moved right 10. So we're going to add 10. So what's -5 plus 10? Well, -5 plus 10 is 5. Let's check. Is that where our domain starts here? Does our domain start at -5? Or, excuse me, at +5? Hey, that's where that first circle starts. 5 plus 10 is 15. Here's 15. Is that where the circle would end on the x-axis? Sure enough, because we moved to the right, so we added 10. So let's type our domain. This time our domain is 5. This time our domain is 5 less than or equal to x, which is less than or equal to 15. Now take a look at how that's connected, because all we did was add 10 to these values, to our x values, because that's what happened up there. So now let's talk about our range. Talking about our range, what happens? Well, this time it says we subtracted 2. So instead of being -5, where does it go? Well, it looks like -5 minus 2 would be -7. -5, -6, -7 is at the bottom. Sure enough, especially if I had drawn my line right. There's -7. And then 5 minus 2 would be 3. And there we have it. So we can see that that window for that second circle is exactly how we thought it would be. -5 minus 2 is -7. So we've got -7 is less than or equal to y, which is less than or equal to 3. Notice that the domain and range changed exactly as the points changed, because we just shifted. The translation in the plane that maps each point onto x plus h and y plus k, where h and k are constant. Doesn't this remind you of vertex form from Algebra 2? H and k are your vertex points, right? So a translation is one type of formation. So remember how we rewrote the ordered pairs? We started with x, y, and then I said, okay, this one moved to x plus 3 and y plus 2. And that's how it worked. So if you want to go back, we actually did that right here. So my new vertex was 2, 0, and that's my h and k. So a translation is one type of transformation. Every translation in the plane can be described by the formula of the form. Now this says x prime. That means the image point. This right here is referring to the image. So the image is x plus h and y plus k. This is your pre-image. X and y are your pre-image, where it started. The translation is a distance-preserving transformation. That is, the distance between 2 points equals the distance between their images. In other words, if we go back to geometry, we're going to know that our points are going to be congruent. I know you can't see that. So the pre-image and image are congruent. That's what this is telling us right here. The translation preserves the distance. It preserves the space. The other thing it tells us, a figure and its translation are congruent. Didn't I just say that? That's because one general definition of congruence is that any figure and its image under a distance-preserving transformation are congruent. They are congruent. The distance between AB is the same as the distance between A prime, B prime. Notice when we did our circle 2 slides ago, or 1 slide ago, the circle size didn't change. That circle did not change at all. If I could draw a circle the exact same size, let's see. And place it on top of the other circle, they are the same. They're the same size. The only thing that changed was their position. Just like if I were standing on the 3rd floor, right here, next to you, and the floor collapsed and I fell to the 2nd floor, I would still be in the same size and shape. I wouldn't lose weight. I might shrink a little in reality, but in truth, it's the same. A line and its translation are parallel. So that means that translations preserve tilt. So the angles are also preserved. So if I take a line and I draw a line and then I slide that line over, so here's my line, and I just move that line. Let's see if I can do this. Okay, if I take this line and I slide it over, they have the same tilt. They're all parallel. I'm just copying the same line over and over again. So, how to come up with these equations? Well, it's very simple. Given a pre-image graph described in a sentence with x and y, the following 2 processes yield the same image. If you replace x with x minus h and replace y with y minus k. So in the actual equation, what's happening here? Well, this is a translation. So if I were to write the translation to this, my translation here would be, oops, cuck-a-boom chicka. My translation here, I had the ordered pair, x, comma, y, and it was being mapped onto, what happened to my graph? Well, it went from, I pointed with my finger, it went from 0, 0 to 4, 0. So I moved it to the right 4, but I didn't move it up or down at all. So my y stayed the same. If you wanted to put plus 0 there, nothing wrong with that. So what happens here is what's h? Well, h is 4. What's k? K is 0. So my original function here was the absolute value function. So if I go back to my original absolute value function, okay, there's my original absolute value function, and the formula says that I replace x with x minus h. Well, h was 4. So I'm going to take this equation, and I'm going to change it, and instead of putting just x in here, I'm going to put x minus whatever h was. In this case, it's 4. Okay? And I'm going to replace y. It says y minus whatever k is. In this case, it's 0, which really means nothing changed for the y values. True? So to simplify this, I could just have y equals what's our domain and range? Well, our domain was all real numbers. Is it still? Sure, our domain's still all real numbers. What's our range? Well, our range was, looking at our card, y is greater than or equal to 0. Did we do anything vertically? No. So it's going to stay the same. Y is greater than or equal to 0. The most confusing part in this is right here when you substitute in the opposite. Okay, so we're going to do the same thing for this equation that we had here. Our original equation was y equals x squared. Okay, well, what's our translation? Well, our translation starts out, we had the ordered pair x comma y, and we're mapping that to what? Well, 0, 0, we went left 3, so that's x minus 3, and then we went up 1, so that's y plus 1. So what are we going to replace x with? Well, this was x squared, true? So that's going to become, over here, we're going to have y. It says plus 1, so we're going to do minus 1. And it had x was squared. We have x minus 3, so you're going to have x plus 3. Helps if I type the x, doesn't it? So we think that this is our equation because of what happened here. Looks like it's good. Check our answers. Now notice this part right here. They simplified it. You can do that. Okay? When you take your test or a quiz, you want to leave your answer in simplified form. Don't ever just stop here. But when you take a park test or something like that, they may show it to you in vertex form. Isn't that what this is? Exactly. Take a look at the same function here. What was our translation? How did we translate this? Well, we started with the ordered pair 0, 0. And we mapped that onto what? Well, we went left 1, so that's minus 1. And we went up 3, so that's plus 3. So my f of x, or my y, is going to start out as y. Instead of plus 3, it'll be minus 3. And then instead of the square root of x, it'll be the square root of x plus 1. I've got to put my square root in there by hand. So we're predicting this. So when we check our answer over here, oh great, the answer is not there. Yep, the answer is not there. We already talked about domain and range for this, didn't we? Domain was x greater than or equal to 0. Now it's x greater than or equal to negative 1. Range was y greater than or equal to 0. Now it's y greater than or equal to 3. Lovely. Now, the scale change theorem is when you're multiplying, okay, when you're multiplying by the scale change theorem, what you want to do is you're going to change to dividing by. So when you substitute into your equation, you're changing it to division. So here's a rule for the scale change theorem. When we look at this particular function, we have y equals the absolute value of x. That's in orange. Our new function is in blue. Well, there's two ways you can look at this, okay? Did our x value change at all here? No. Did our y value change? Yes. What happened to our y value? Well, our y value got multiplied by 3. So one of the rules for the scale change could be we had xy, and that was mapped onto, the x stayed the same, and the y was multiplied by 3. True? Yeah, that could be true, Miss Finney. Good job. So if we do it that way, when we look at our equation, nothing changes on the x, but our y, when we type it in, it's going to be y divided by 3, because you do the opposite, equals, you know what, let me go to the equation editor, because that'll just be easier. So I'm going to go to my equation editor, and I'm going to have y, I want to put a fraction. There it is, fraction. I'm going to have y divided by 3 equals the absolute value of x. One thing I don't like about the equation editor here is that line doesn't show up very well. Well, if I solved this for y, like they did on the translation ones, we would multiply both sides by 3. So our final answer would just be a y on this side, and we would have a 3 on the outside of that absolute value. And that would be our final answer. So that's one way you could write the equation. Another way you could write the equation is say, hey, well, what if I want to compare y values? These two y values have the same thing. True? All right. So if that's the case, what happened to my x's? Well, my x was 6, and now it's 2. So it divided by 3. Yes? So I have my ordered pair here. I started with x comma y, and I mapped that onto x divided by 3, and the y stays the same. Well, what happens to my graph then? Well, for my graph, or for my function, if I go back to y equals, does anything get changed on the y? No. X was x divided by 3, so when I actually put this in, it's going to be 3 times x. Guess what? When you graph both of those, you're going to get the same thing. So when you're doing these, lots of times students will say, well, so which one's right? Well, they both are. And you're fortunate in that you can trust your teacher to know both answers. Okay? Taking a look at the same thing for the parabola here. Same thing for the parabola. Well, we had 2, 2, and it went to 2, 4. I'm sorry. We had 2, 4, and it went to 2, 2. All right, so what happened? Well, the x's stayed the same, but the y's changed. All right, we can do that. So if the x's stayed the same and the y's changed, we started with an ordered pair, x comma y. And that gets mapped onto. Did the x change? No. Did the y change? Yes. It was 4. Now it's half of that. So it's y divided by 2. So what would our equation look like? Well, instead of just y, we're going to have 2y equals, does anything happen to x? Nope. X stays the same. So we have x squared. But again, we probably want to solve that for y. So that means our equation would be y equals, and again, let me just go back to equation editor so I can get the fractions. So y equals, now that I know where the fraction is, x squared and it was 2 times y, so now it's going to be dividing on both sides. And there's your answer. I like to make sure that line shows up. It's just kind of odd sometimes. Well, Miss Finney, that's great, but what if I wanted to compare the y values and they're the same? Well, if the y values are the same, you do it the same way, folks. X comma y gets mapped onto, oops. Well, what happened to our x? Our x was 2, and now it's 4. So we doubled that. What happened to our y? Well, our y was 4, and now it's the same. Okay, so as I'm checking this out, what's my equation going to look like? Well, my equation is going to be, does anything change on the y? No. Nothing changes on the y. So I have y equals. It said 2x. Well, what's that going to look like in my function? Well, I'm going to have x divided by 2, and that's all gets squared. All of the equation editors are different, folks. It's just like when you're checking out with a credit card. Guys, this was wrong. That should have been a 4, because this is a 1. You would have told me that if I had been listening to you. So this should be a 4 here. So this should be a 4 here. And then when we simplify this, we get the same equation. Yeah, that's another difficulty with me not actually being there, is I make mistakes and you don't catch them. I hate that. But I'll be back and you'll be able to catch all of my mistakes. So no matter which way you do it, you're going to get the same answer. Do you see what I'm talking about here, folks? This ordered pair right here, this is 2, 1. I was reading the ordered pair. I thought it was 2, 2, instead of actually counting the ordered pair. Now, does our y change? No. Does our x change? Yes. It was 1. It's now 2. So let's take a look at our graph, our translation. We started with x comma y, and that, oh, cock-a-boom chicka, comma y, and that got mapped onto, well, we doubled our x, and we left our y alone. So when we look at our equation, in our equation editor, look at our equation, we're going to start with y equals the square root of, it says x, but our x, we said we doubled, so this time it's going to be x divided by 2, because you plug in the opposite. And there's your answer. No other way to look at that, folks. It's the only option. Okay, so here's our transformation, and they're asking us to sketch it. So if we first graphed, we had 0, 0. We had the square root of 0 is 0. We had the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. So we have what looks like this. So now what they want us to do is, it's going to be 1/3 of x each time. So, when we graph this, what's it going to look like? Well, our x's are going to be closer and closer, true? So instead of 1 being 1, it's going to be 1/3 being 1. So 1/3 would be 1. Instead of 4 being 2, it would be 4/3 being 2. Instead of 9 being 3, it would be 1/3 of 9, which is 3 being 3. Instead of 16 being 4, it would be 16/3, so a little bit beyond 5 would be 4. And so our graph would look something like this. And you can check this by using your calculator. Okay? Well, that pretty much does it for today. So, with the time you have left, I'm going to ask you to start on your homework. There are books in the closet, and you can work together to answer the questions, and even have the substitute check off the homework for you if you get it done. Okay? Thanks. Bye-bye now.